So in our wave on a string lab, we saw that the geometry of the string, which on a guitar is held fixed at the bridge and at the fret, determines what waves are possible. Any wave that's got no motion in those two places is okay. These large standing waves only exist for certain frequencies because you need to be sending them in at the exact right frequency that when they reflect off the boundaries, they overlap themselves and build up. You need to have that kind of constructive interference. So we've gone through the patterns of that. Essentially, the lowest frequency wave that fits in, the one bump wave, the fundamental. On a guitar string, multiples of that are all allowed too. In a real guitar string, if you pluck it, it's going to play all those notes at once. And that's why there's that nice rich sound. So when you pluck a guitar string, it plays all the allowed frequencies, or a lot of them. And if you played any of those frequencies, you would notice the guitar strings start to vibrate. That's how a sitar works. It has some strings that you don't pluck. They vibrate in response to the ones you do pluck. So this isn't just true for guitar strings. Any device that works by striking, plucking, or blowing on it, and a noise comes out of it, basically has the same thing. There's some sort of natural frequency, there's some wave that develops in the unique geometry, and what waves can go are limited by what the geometry is. So one of the most famous examples of this are these devices, which are called tuning forks. For electronic tuners, these were one of the best ways to get a note. And you strike them with the mallet, and you probably can't hear that. It is vibrating when I look at it, and I can feel it vibrating. I can sort of hear it up near my ear. But one kind of cool thing happens when I put it up to the board. I suspect you could hear that. And what actually was happening, when it was just vibrating on its own, it was only the air molecules close to it that were set into motion by the vibration. When I put it on the board, all the air molecules close to the board all the way around, they were set into motion too, made the sound louder. So this tells me it was 341.3 hertz. It was an F. And that note is being played by it because of the geometry of this. If I pick a fork with a different geometry, this one's bigger, I'll get a different note. And I think you could hear that it was lower pitched. And we'll talk about why that is later. But basically, larger wavelengths were allowed in this case. If I pick a much smaller one, I get a very high-pitched noise. So we are not going to look at the geometry of tuning forks as part of this class. We're going to specifically focus on waves on a string, open organ pipes, and closed organ pipes. But in all cases, essentially the same physics are going on. You've got waves trapped due to certain boundary constraints. Is there fixed or moving medium at the end of the instrument?